In this section, we're going to talk about basic rules of differentiation. First, we're going to expand upon our concept of a derivative and create what's called a derivative function. So suppose we have a function such as f of x equals 2x squared plus 1, and we want to find the slope of the tangent line at three different places: x equals -2, x equals 1, and x equals 3. Based on our current approach, we would have to evaluate the limit at each of these points. Here's the limit that we were using. We could also use the one involving delta x's. But just to remind ourselves how that process works, let's do this starting with the first value. So if I have to determine the slope of the tangent line at -2, then I would be evaluating the limit as x approaches -2 of f of x minus f of -2 divided by x minus -2. Start plugging things in, and we have the limit as x approaches -2. The function itself, f of x, is 2x squared plus 1. And if I evaluate 2x squared plus 1, I'll come off to the side and do that. So f of -2 would be 2 times -2 squared plus 1. 2 squared is 4. 4 times 2 is 8. And 8 plus 1 is 9. And that's divided by x minus a -2, which is the same thing as x plus 2. So next, we start expanding the numerator, combining like terms, that sort of thing, which would give me 2x squared, positive 1, -9 would combine to -8. And the reason I'm going through this process is, at this point, if I plugged in -2, you can try it yourself and see, you would get 0 divided by 0. So we need to continue with some algebra to try and evaluate this limit analytically. In the numerator, I could factor out a factor of 2, which leaves me the quantity x squared minus 4. But that will factor into x plus 2 times x minus 2. Which is nice because I also have this factor of x plus 2 in the denominator, and that term, x plus 2, can cancel away. What that means is I'm left with the limit as x approaches -2 of 2 times x minus 2, and at this point, if I plug in -2, I get an answer. 2 times -2 minus 2 would be 2 times -4, or -8. So the slope of the tangent line at -2 is -8. Now, suppose I want to come up with it at the other points, 1 and 3. I just need to go through this entire limit process all over again. Which it isn't all that bad for one point, but if you have to do multiple points, it can get a little bit intensive algebraically, just with all the steps involved. So, what we're going to do is try a different approach. And this new approach would be to try and calculate the derivative without plugging in a point of interest. The result then should be a function which would represent the value of the derivative at any point. So I'm going to switch and use the difference quotient here, but you could still use the limit from the previous slide. But that's what we're going to try. We're going to take our function 2x squared plus 1 and evaluate the derivative function by not plugging in -2 for x or any other value for x. We're just going to leave x alone and see what happens. So we did some problems earlier in the class with evaluating difference quotients, and that's sort of training you on how these are done. And that's exactly why I did that. So what we're going to do now is take what we know about the difference quotient and try and apply that to this limit. So let's see what happens. Now the trickiest thing here is generally evaluating f of x plus delta x. So let me do that off to the side first. So if f of x is 2x squared plus 1, then f of x plus delta x, what I do is I'm replacing x with the quantity x plus delta x. So everywhere I see an x in this function, I'm going to replace it with x plus delta x. So what that means is, at that point, I would need to expand this binomial, and I could use FOIL to help me out there. But that's what it means to evaluate the function at f of x plus delta x, which is really the first part of this limit. So this would be the limit as delta x goes to 0, f of x plus delta x minus f of x, so just subtract the function itself, divided by delta x. And we're trying to observe when delta x goes to 0. All right, in the numerator, what I need to do is expand x plus delta x using FOIL. And you can do that with FOIL, or you can use your formula for the sum of squares to speed things up, and that's what I'm going to do. So it's the first item squared plus 2 times the first times the second plus the second item squared. Then I have plus 1, and then a negative which needs to distribute to both items in this binomial, so minus 2x squared minus 1. All right, so I have some things that will cancel. Here's a positive 1 and a negative 1. That's great. That's anything that cancels away is a good start. We do need some more things to cancel, however, before we can take the limit, because at this point I would still end up with 0 over 0. Distributing the 2 would give me 2x squared plus 4x delta x plus 2 delta x squared. And then I still have this minus 2x squared hanging out all over delta x. And this is nice because here's a negative 2x squared and a positive 2x squared. Those will cancel. If you get a lot of things canceling in this process, you're on the right track, because that's generally what needs to happen before the limit can be done. In the numerator, it appears that I have a common factor of delta x in both terms of the numerator. I'm going to factor that out, which would leave me 4x plus 2 delta x. And there, that reveals a factor of delta x in the numerator and denominator that can cancel. So I now have the limit as delta x goes to 0 of 4x plus 2 delta x. And as delta x goes to 0, so I'm taking my limit this time, if delta x goes to 0, this whole term is just going to go to 0, and the result is going to be the function 4x. So what I have here is a derivative function, f prime of x equals 4x. So what that means is I can now evaluate my derivative at any point x simply by multiplying it by 4, And that would be equivalent to going through this entire limit process at each one of those points individually. So going back to the points that we had in the previous slide, here's all I need to do. So if I want to find the slope of the tangent line at x equals -2, then I just need to find the derivative function evaluated at -2. So 4 times -2 is -8. That's incredibly much faster than going through an entire limit. And if you have other points, all you have to do is just plug those points in. So f prime of 1 would be 4 times 1. So the slope of the tangent line there is 4. And when x is 3, f prime of 3, the slope of the tangent line at x equals 3, is 4 times 3, or 12. Even though it takes some time to evaluate the limit and come up with a derivative function, it saves you a lot of time later on if you have multiple points that you need to find the slopes of tangent lines. So you can definitely see a huge advantage in coming up with this derivative function. But it still isn't all that easy to come up with the derivative function through this limiting process. So what we're going to do next is try and come up with ways of determining a derivative function easier by looking at different types of functions and how this limit would actually work out for different types of functions. So let's begin with a constant function, which is f of x equals c. C could be a value 2, it could be a value -4, 3/5, any number, any real number. So it's just a constant. We know that the graph of a constant is a horizontal line. And what we're going to do is come up with the derivative of this constant function using our limit definition and see what happens when we evaluate it for any constant. So the thing that we need to understand is no matter what we put in for x in a constant function, the output is always whatever this constant is. So similarly, if I try and evaluate f of x plus delta x, it doesn't make a whole lot of difference. The result is still just that constant c, whatever this number happens to be. So anything I put into f, the result is just c. So the derivative of a constant function would be the limit as delta x goes to 0. F of x plus delta x evaluates to the constant c. F of x evaluates to the constant c. And then we divide that by delta x. Then this is the limit as delta x goes to 0. C minus c is 0. And it may look like this limit's going to result in 0 divided by 0, but it actually doesn't, because we don't take the limit at this point. What we do is we divide 0 by delta x. So 0 divided by any number is defined. It's just plain old 0. When you have 0 in the denominator, that's problematic. 0 in the numerator is okay. 0 divided by anything is just 0. So now when I take this limit of just 0, the result is 0. So what that means is for any constant function, f of x equals c, the derivative of that function is just 0. Now a different way that you might see that written could look like this. So dx of c is equal to 0. So d dx, that's just another way of saying the derivative of the function c with respect to x is equal to 0. So that's just a rule stating that the derivative of a constant function is 0. Now, what I'd like you to see is the mechanics of exactly why that's going to be 0. So let's take a look at this in a couple different apps, starting with an app for bubble charts, and we'll take a look at what happens. Okay, so here I have the function y1 equals 3. You can see that up here in this chart. So all I've done is put in a constant function y equals 3. If we look at the bubble chart over here, what this is doing is for every single value of x, and I've set it to just pick points every quarter of a unit. So it takes a value of x, plugs it into the function, and gets the output value for y. But since this is a constant function, anything that I put in for x is just the output value 3. So going from -5 all the way over to +5, every single output value of y is just 3. Now, if you graph that, so if you graph those points, that's what those points look like. And in order to produce a graph, we obviously just connect the dots here and create a graph which comes up with this horizontal line. And the thing that is the same about every single one of these points is that the y value is always 3. All right, so if I show you the graph here, that's the graph itself. So every single y value is 3. That's what it means to be a constant function. Now, this term right here, delta y1. So delta y1 means the change in the y values for what I've determined as y1. And I allow for 2 different functions to compare, but we won't do that in this example. It just means you take y2 minus y1. So for instance, if I take these two y values, the change from one y value to the next would be 3 minus 3, which is 0. And if I allow the function to show us all the different values of delta y1, that's what we see. The change from one y value to the next is always 0 because the y values never change. And what we're doing in calculating a derivative is we're looking at slopes. So we're looking at slope, which is a measure of the change in the y divided by the change in the x. So the change in the y is always going to be 0 in this particular function. The change in the x I've set to a quarter of a unit, so it changes 0.25 each time. Well, 0 divided by anything, as we just explained, is 0. So the slope of all the tangent lines is going to be 0 when we have a constant function. That's what's being described here. Let's see what happens if we apply the same ideas to a linear function. So y equals mx plus b. Well, we would need to find the first derivative, we would need to do the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So this would become the limit delta x goes to 0. F of x plus delta x means I would just replace my x in my linear function with x plus delta x. So it's going to be m times x plus delta x plus b minus the original function itself, which is mx plus b. So what I can do for simplification is do the limit as delta x goes to 0. I can distribute my m in the numerator, which would give me m times x plus m times delta x plus b. And then I also need to distribute that negative, so minus mx minus b. And that's all going to be over delta x. Now, what you can see is a lot of things that cancel. And if you get a lot of things that cancel, you're on the right track. Negative mx, positive mx. Negative b, positive b. Those four terms cancel, leaving us with the limit as delta x goes to 0, m delta x over delta x. And I have a shared factor of delta x in the numerator and the denominator, which can cancel away. So now this becomes the limit as delta x goes to 0 of m. M is some constant. It's the slope of this line. It doesn't depend on delta x in any way, so this is just the limit of a constant, which just results in the constant itself. So the slope of a tangent line for any line is just equal to the slope of the line itself. That may sound obvious, that may sound confusing. Either way, I think we can shore up what's happening here in the Bubble Charts app and really kind of see it. But the thing to take away is whenever you have the derivative of any linear function, its derivative is just the slope of the line. Notice that b would have been a constant in that equation, and b disappears through the differentiation process. So just like before, we saw a constant function, its derivative is 0. A linear function, its derivative is its slope, so just an m is what we result with. Okay, so what I have here is the equation y equals negative 2/3 x minus 1. So I've got a slope of negative 2/3 and a y-intercept of negative 1. Now, what the computer is doing for us, again, I'm using delta x as 0.25, so the difference from one x value to the next is a quarter of a unit. So we go from negative 5 to negative 4.75, negative 4.75 to negative 4.5. So it's just off by a constant of 0.25. What the computer then is doing is evaluating the function at each one of those points. Sometimes it ends up with a decimal because the negative 2/3 of the value minus 1 would result in a fraction. Sometimes it ends up being an integer. It doesn't really make a whole lot of difference. What we see, however, is a set of points that can be plotted on this graph, and you can see those points. So now I've just taken each of these coordinate pairs and just plotted them somewhere over here. Okay. All of these points line up in a nice linear fashion. It's the graph of a line. We should, of course, expect that to occur. Now, so from the points, that's where we get the graph. So here's the graph. And if I take the difference between any two y values, so the difference between any two y values is delta y. Delta y is y2 minus y1. So if I take 2.1667 minus 2.3333, so the difference between these two, that's going to give me my first delta y1. And I could check that on a calculator. Let's see, it would be 2.1667 minus 2.333, so negative 1.663. All right, so now I'll try negative 0.1663 it was. So now I'll show the delta y values, and what the calculator has, or what the computer has done now, is calculated each of these delta y's for us for each two corresponding numbers. Now you'll see there's a slight difference in what I have and what the calculator has, and I'm sorry, the computer has. And the reason that there's a slight difference there is I've rounded 2.1667 to 4 decimals, but the computer is actually storing that to a lot more decimals, so it's just rounding error. It is the same value, it's just rounding error. All right, but that's where those numbers are coming from. What I want you to notice here is that the value for delta y is the same at every single point. So if you go from one y value and add this number, which if you're adding a negative, it's subtracting obviously, it brings you to this value. If you add this number, it brings you to this value. If you add this number, it brings you to this value, and so forth. That's what this delta y is kind of doing for us. The thing is, the difference between these numbers is the same value at every single point. So if I bring up these points here, for instance, and whatever the y value is of that, if I take its y value and subtract 0.1667, I'm going to get the y value of this next point. If I subtract 0.1667 from that, it'll give me the y value of the next point, and so forth. The y values changing at a constant rate is what's really the driving force behind a line, is that the change from one point to the next vertically is identical from every single step. So if you look at where this number comes from, let's look at the slope. If I take negative 2/3, that's negative 0.666667. But that's different from the delta y that we have, which is negative 0.16667. What's the difference? Why are we getting a different answer? Well, the thing is, the slope of a line is defined by the change of the y values divided by the change in the x values. So the change in x values is 1/4 of a unit in this particular case. And I did that on purpose because I'd like to have a lot of points that you can observe, but not too many. So I used 1/4 of a unit of difference in delta x. Each 1/4 of a unit of difference in delta x results in negative 0.1667 units of change in the y. So let's check that out. So negative 0.1667 divided by 0.25. There we have negative 0.6668, which again, it's accurate to 3 decimal places because the numbers I'm using are accurate to 3 decimal places. But that's where the slope is coming from. If I had done delta x as 1, then delta y's become the slope then, because now if delta x is 1, then the slope is just whatever delta y is. So that's why I would have negative 0.667 divided by 1, which is just negative 0.667, which is the slope. But the most important thing to remember is The defining aspect of a line is the constant change in the y values with respect to a constant change in the x values as well. That's what makes the graph a line versus any other type of shape. And that's why when we calculate the derivative, which is a measure of how quickly the y values are changing with respect to x, results in a constant value. So for any linear function, the derivative is just its slope. Now let's take a look at a quadratic, see what happens there. The derivative of a function f that's quadratic would be the limit as delta x goes to 0, a times x plus delta x squared plus b times x plus delta x plus c minus the original function ax squared plus bx plus c all over delta x. As you can see here, the higher degree we have, the more complex this operation is going to get. But it isn't too bad with a quadratic, so let's get started. First things first, I need to square this x plus delta x business. So square of the first plus 2 times the first times the second plus the square of the second. I can distribute the constant b into these parentheses and get bx plus b times delta x, then plus c, and I can distribute that negative and make negative ax squared minus bx minus c all over delta x. Now, a couple of things look like they will cancel. I have a positive bx and a negative bx, positive c and a negative c. Those will cancel. If I distribute this constant a, that should reveal some more things that will cancel. So ax squared plus 2ax delta x plus a delta x squared plus b delta x minus ax squared all over delta x. Now I have an ax squared and a negative ax squared that cancel each other out, and a whole bunch of terms remaining that all have a factor of delta x in them. So I'm going to factor that out in the numerator. So that would leave me 2ax plus a delta x plus b all over delta x. So the factor of delta x in the numerator and the denominator will cancel each other out, which leaves me the limit as delta x goes to 0 of 2ax plus a times delta x plus b. And when I let delta x go to 0 at this point, that makes this term go to 0. So the result is 2ax plus b. So this is effectively a linear function. So 2ax can look like something of the form m times x plus b. So effectively, the derivative of a quadratic is a linear function. So what that would mean is the change in y with the quadratic is going to be linear. So the values change at a constant rate. Now, as I mentioned, with each increase in degree from one polynomial to the next, we get quite a bit more complexity in evaluating that limit. But you probably have noticed at least something that is similar among those changes. So for instance, degree 0 polynomial is a constant. So if you take a degree 0 polynomial and you find its derivative, you get 0. Okay? A linear is a degree 1 polynomial. If you take the derivative of a linear, you get a constant, which is a degree 0 polynomial. If you take a degree 2 polynomial, which is a quadratic, and you find its derivative, you get a linear, which is a degree 1 polynomial. So each iteration of finding a derivative is bringing the degrees of a polynomial down by 1 each time. So that should help you sort of come up with an idea of how to do this in general. So because the degree of each polynomial seems to be reducing by 1 when finding the function's derivative, that observation leads us to one of the most important rules of differentiation, which is called the power rule. And the power rule states this: the derivative with respect to x of x to the nth power is n times x raised to the n minus 1. So effectively what we're doing is whatever this value is right here, we bring it out as a constant multiplier and reduce the degree of the polynomial by 1. And we can do this term by term, which will establish a rule that allows us to do that in a little bit. Right now we're going to just establish it for one single term. Now, in general, n can be any real number. So the value of n can be an integer. It can be a positive integer. It can be a negative integer. And it could be fractions. That's fine as well. Or it can be an irrational, and that's okay. It also technically even works for 0, but if 0 is your exponent, then x to the 0 is 1, so you're actually dealing with a constant function instead of a polynomial. We're going to do a proof that proves this for positive integers. The proof for any real number involves more complex mathematics that we don't have at this point. So we'll do a proof that shows how this process works for positive integers and just assume that it works for real numbers as we go through examples. So let's get started. So a proof is what gives us the details as to why something works. And in mathematics, we need proof, because if we're going to rely on a rule, we need to know that it works. We need to know that it works every single time. So to do this, what we're trying to do is find the derivative with respect to x of the function x to the nth power, which is just another way of asking for f prime of x if f of x is x to the nth. So to do this, we must do our limit as delta x goes to 0 of x plus delta x raised to the nth power minus x to the nth power all over delta x. Because my function is x to the nth, if I evaluate that at x plus delta x, I get x plus delta x in parentheses raised to the nth minus the function itself. So that's where I'm at right now. Okay, if n is known, so if it's 1, 2, 3, 4, 5, if it's a known value, we can expand x plus delta x to whatever that value n is. If it's an unknown value, we still can, but we have to kind of take some general liberties here. When you're expanding a binomial, whether it's to the second power, to the third power, fourth, or whatever, It's dictated by a rule based off of Pascal's triangle, if you've seen it. It's called the binomial theorem. And you may not know the details of the binomial theorem, and that's okay. We can get through this proof without you knowing the details of what happens there. But what would happen if we tried to expand x plus delta x to the nth power is something like this. You always end up with the first term as x to the nth power. And the next term is n times x to the n minus 1th power. But that gets multiplied by your second term. So n times x to the n minus 1 times delta x. The next term is a combination of n items taken 2 at a time, and you may not understand combinatorics at this point, and that's also okay. If you've taken a stats class, it's the combination function that you learned in statistics. But for right now, it's not really a necessary piece for you. But it's n choose 2 x to the n minus 2 times delta x squared. The next one is n choose 3 x to the n minus 3 times delta x cubed. And this process continues until you get to the last term, which is just simply delta x to the nth power. Okay, so that's the expansion of a binomial to some unknown power. Now, if we subtract x to the nth from that and divide by delta x, there is things that you can follow along here that happen in every single binomial expansion. So number one, if you'll notice, x to the n is positive over here and negative over here. Those cancel. That's simple enough to understand. In the next stage of the process, all the terms in the numerator have a factor of delta x left over. And we saw this in the examples that we did. We then factored out that remaining delta x term. So that leaves n times x to the n minus 1 plus n choose 2, whoops, I don't mean divide, n choose 2 x to the n minus 2 times delta x. And then all the terms in between lose a delta x as well. Then plus delta x to the n minus 1, because the last term loses a delta x also, because it just got factored out. But there's this factor of delta x in the denominator. That one can cancel out the one in the numerator, leaving us with the limit as delta x goes to 0 of n times x to the n minus 1 plus n choose 2 x to the n minus 2 times delta x plus all those terms in between plus delta x to the n minus 1. Now, every single term that has a delta x is going to go to 0 at this point because we're going to take a limit. So even though we don't know what n choose 2 is maybe, it doesn't matter because all of that's going to get multiplied by 0, which takes that entire term to 0. All of these terms in between have a factor of delta x in them. They all go to 0, including this last term. So all of these terms go to 0, leaving us just with the limit as delta x goes to 0. Well, actually, I took the limit because I let all those delta x's go to 0. So it's really just the remaining factor, n times x to the n minus 1, which finishes off the proof. Okay, that was a lot of work. But it establishes that we can find the derivative of any polynomial function or any value that has an exponent, or any variable that has an exponent using the power rule. So let's see how we can apply it. It's going to make our lives much easier. Now, f of x equals x cubed. if I was going to find its derivative using the limit process, I could go ahead and get started and go through the entire limit. However, with the power rule, what we can say is the derivative of this function is going to be, so we bring the exponent down as a multiplier. We multiply it by x times 1 less than the original exponent. The derivative is 3x squared. We're done. That's all we have to do. That's much more enticing of an operation than going through the entire limit process every single time. That's why we took the time to do what we did. As I mentioned, the power rule can be applied with non-integer values of your exponent as well. So if you have f of x equals x to the 2/3 power, its derivative then is going to be 2/3 x to the 2/3 minus 1. And when I do 2/3 minus 1, I just have to make sure I'm using rules of fractions here. So 2/3 x to the 2/3 minus 3/3 would be negative 1/3. And there aren't a lot of rules of simplification, but in general, the rules are, number one, make sure you don't have any negative exponents in your final answer. So you could write this as 2 over 3 to the x to the positive 1/3. Or if you want to change that into a radical because it's just x to the 1/3, which would be the cube root of x, that's fine as well, but not as necessary. If it's a square root, generally it's considered simpler if you go ahead and change the square root into the radical, but any other root you could leave as a rational exponent. Next up, f of x equals 1 over x squared. This looks a bit more complex until you remember that you have rules of exponents to work with. And the rule of exponents that's going to help you here is if you want to bring that x squared up into the numerator, you can do that by simply making it a negative exponent. So x to the negative 2. Now the power rule applies because you have some variable x raised to an exponent. Bring the exponent down and subtract 1 from it. So negative 2 minus 1 is negative 3. And just simplify. And again, simplify definitely means take care of those negative exponents. So, and all you have to do is write this as negative 2 over x to the positive 3rd. And you're done. The constant multiple rule. So suppose we have a function f of x, which could be linear, quadratic, or any other type of function, even cosine x, sine x, really, but it has some multiplier c. The rule is the derivative of some constant times any function is just equal to the constant times the derivative, which effectively means you can ignore constant multipliers and just do the derivative of the function to make everything a little bit easier. So let's see how that works out, and we do a proof. So it would be the limit as delta x goes to 0 of the constant c times f of x plus delta x minus the constant c times f of x all over delta x. So the constant c ends up in both of these terms in the numerator, which you can factor out. And when you factor out of the numerator that constant c, you can actually factor it out of the entire limit. So you end up with just c times this limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, which is just c times your derivative. So you can take the constants out and then do your derivative to make things easier. So let's look at a couple of examples of this. So let's find the derivative of y equals 3x squared. So the derivative of function y could be 3 times the derivative of x squared, which would be 3 times, we bring the 2 down, and subtract 1 from the exponent. So 3 times 2x to the first power, or 6x. And absolutely, you could have just brought the 2 down and multiplied it by the 3, and then subtract from 1. That's fine as well. However you want to speed this up is perfectly fine. Here's another example. In order to do this, you need to bring x cubed up into the numerator. So 5x to the negative third power. So y prime would just be negative 3 times the 5, so negative 15, x to the negative 3 minus 1, which is negative 4, or negative 15 over x to the fourth power. Now let's take a look at the sum and difference rules. So if f of x and g of x are two differentiable functions of x, then the derivative of the sum or difference of those two functions is just the derivatives, or the sum of difference of the derivatives. So to prove this, let's just let h of x be f of x plus g of x. And I'm going to only use plus here instead of plus or minus. If it works for the sum, it also works for the difference. So h prime of x then would be the limit as delta x goes to 0 of h of x plus delta x minus h of x all over delta x. But since we know h of x is f of x plus g of x, then we have effectively f of x plus delta x plus g of x plus delta x minus f of x plus g of x. Running out of space there. Get another parentheses in. Great. Divided by delta x. If I distribute that negative, then I have the limit as delta x goes to 0 of f of x plus delta x plus g of x plus delta x minus f of x and minus g of x. You probably can see where this is going at this point. Since these are both differentiable functions already, we can rearrange these limits in any way that we want. In fact, we can even break the numerator up into separate limits if we like. So I could make this the limit as delta x goes to 0, and I could take the two terms involving f of x, as long as I have them both still divided by delta x, in one limit, and then the two terms involving g of x in one single limit, which means that I have the derivative of f plus the derivative of g. So if you want to differentiate a sum, that's perfectly okay, or a difference as well. So to see some examples, let's find the derivative of 2/3 of x cubed minus 2 times the square root of x. Now, you often will want to do some pre-processing, which means rewrite everything in terms of a power because right now all we have established is the power rule of differentiation. So in order to use that rule, you have to write things with an exponent. Once that's done, then to find the derivative of your function, sorry about that, let me fix that. So f prime of x would be 2/3 times 3x squared, so bring the 3 down, subtract 1 from the exponent, minus 2 times 1/2 x to the negative 1/2 power, because 1/2 minus 1 gives me negative 1/2. Now we simplify. So if you'll notice here, 3 and the 3 there cancel, 2 times 1/2 cancels, so this could be 2x squared minus, instead of x to the negative 1/2, I could make that 1 over x to the positive 1/2, which is the square root of x. And there's my final simplified answer. Next up is the product rule. When it comes to finding derivatives of products of functions, the process is actually slightly more complex than simply finding the product of the derivatives. So let's take a look at an example and see what that means. So I have a function f of x, which is 3x squared times the quantity x cubed minus 2x. I want to find its derivative. First, I'm going to expand the binomial and then use the power rule. Then we can establish what the actual derivative is. All right, so f of x can be written as, so I would take 3x squared times x cubed to get 3x to the 5th power. Then 3x squared times negative 2x would be negative 6x cubed. Both of these I can easily apply the power rule to. So the derivative of f is 15x to the 4th, because I just brought the 5 down, multiplied it against the 3, subtract 1 from my exponent, minus 18x squared. So there is my derivative. Now, I'm going to try it in a different way. I'm going to try it by not expanding first. I'm going to try it by multiplying, just leaving it as the product of two separate functions. So I have f of x, and I'm going to call it the product of the functions h of x and g of x. H of x is going to be the first of these two products, so the 3x squared. G of x is going to be the second, which is in parentheses there, x cubed minus 2x. And what I'm going to do is find the derivative of each one of those separately. So let me separate my real answer from what I'm going to get over here. So h prime of x would clearly be 6x. G prime of x, using the power rule, would be 3x squared minus 2. Now, if f prime of x were the product of these derivatives, then we could look at h prime of x times g prime of x. That would be 6x times the quantity 3x squared minus 2. That gives me 18x cubed minus 12x, which is not at all the same as 15x to the 4th minus 18x squared. And at this point in time, I get a lot of students who try and say, oh, well, maybe if we modified it this way, maybe if we just didn't do this part, and they try and come up with some way of determining. You just need to learn the product rule. The derivatives just don't work this way. You can't take the derivative of the first item in the product and multiply it by the derivative of the second item in the product. It just simply doesn't work. Okay, so let's establish the product rule and see what it tells us to do. So the product rule, what it says is this. The derivative of a product of two functions is the derivative of the first function times the second function plus the first function times the derivative of the second function, which looks crazy. I understand. But let's use our example and just see that it works. All right, so I would have the first function as my 3x squared. The second function as the x cubed minus 2x. All right, we have the derivative of the first. We already established that as 6x. And we have the derivative of the second. That was already established as 3x squared minus 2. So in order to use the product rule, what it says is to take the derivative of the first function, which would be 6x, multiply that by the second function, which was x cubed minus 2x. So it's not the derivative of the second at this point, it's just the second function. Plus the first function, which is 3x squared, times the derivative of the second, which is 3x squared minus 2. Now, if we expand and simplify, let's see what happens. 6x times x cubed is 6x to the fourth power. 6x times negative 2x would be negative 12x squared. 3x squared times 3x squared is 9x to the fourth. 3x squared times negative 2 would be negative 6x squared, which ends up giving us 15x to the fourth power minus 18x squared. The exact same thing that we got back when we multiplied out using binomial expansion. So the product rule works, but we have a couple of questions. A, why would we do that? Because if we can just expand the functions in the first place, why wouldn't we just expand the functions to begin with? And the answer to that is, when you have polynomials, you absolutely can expand. But if you have functions that are not polynomials, like sine of x, the natural log of x, e to the x, you can't necessarily expand first. So there are times when you have to have a product rule. Secondly, why does it work? Well, let's do a proof and try to establish the reason why it works. Now this proof will take a little bit of time, so let's just kind of get comfortable here and see how it works out. We'll begin by letting f of x be the product of two functions. I'll call them g of x and h of x. So the derivative of f of x we would know to be the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. That's well established as the definition of a derivative using limits. Now, what we know is a little bit about how f of x is defined. It's defined as the product of g of x and h of x. So g of x plus delta x times h of x plus delta x minus, and then just the function itself, which would be g of x times h of x all over delta x. Okay. Now, that as written doesn't enable me to split this limit up in any specific way to make two separate derivatives, which is why I'm not able to just take the product of the derivatives in the end. What I have to do is I have to insert a term that doesn't exist already to make this limit work the way that I want it to work. And this type of proof is one of the most difficult types that we have, where you have to make up a term that doesn't exist rather than canceling out terms that already exist. How do people come up with this? Well, they just try different things until they find the thing that actually works. Sometimes it takes a long time. Some proof take hundreds of years to establish. Sometimes it's obvious and it only takes a little bit of time. But in this case, what I have to do to make this limit work is insert a couple of terms. So what I'm going to do is I'm going to leave the first term as is, g of x plus delta x times h of x plus delta x. I'm going to then subtract g of x times h of x plus delta x. But I can't simply subtract that term from my limit without also adding the same thing. So adding g of x times, h of x plus delta x. And then I still have this minus g of x times h of x all the way down here at the end. All of this is going to get divided by delta x. And you may be thinking, why on earth would I insert those two terms? How could I possibly come up with those? You don't have to come up with these. I'm showing you the proof of how this works, and you just need to follow along and understand that the product rule does work every single time as expected. That's the point of the proof. So the reason that I chose this term is in the first two terms, so here and here, I have a common factor now. And that common factor is h of x plus delta x. And in the second two terms over here, I also have a common factor. That common factor is g of x. So what I can do is factor those out, which lets me rewrite this limit a little bit. So if I factor h of x plus delta x out of the first two terms, that leaves me g of x plus delta x minus g of x. And if I factor g of x out of the second two, then I have g of x times the quantity h of x plus delta x minus h of x. Everything is still divided by delta x. Okay. Now, this gives me the sum of two items. I can always split up a limit about a sum. That's perfectly fine. So I could rewrite this as two different limits. So the limit as delta x goes to 0 of h of x plus delta x times g of x plus delta x minus g of x all over delta x plus the limit as delta x goes to 0 of g of x times h of x plus delta x minus h of x all over delta x. Now, the reason that that's important to do is this. In the first limit, as I let delta x go to 0, when I let delta x go to 0, this portion over here, that's exactly g prime of x. So all that together becomes the derivative of the function g. Over here, when I let delta x go to 0, h of x plus delta x just results in h of x. So when I take this limit, I get h of x times the derivative of g of x. In the other limit, first off, g of x is not dependent at all on delta x. At this point, we can really look at it as just a constant. So g of x can be pulled out of that limit altogether, leaving us with these terms over here, which those altogether make up the derivative of the function h. So that's times h prime of x. That right there establishes our product rule and why it works. As you might expect, where there's a product rule, there's also a quotient rule. And that is the case here. So if we need to differentiate a function that involves a quotient, we can't simply differentiate the numerator and denominator of the quotient. We have to follow this particular rule. So the derivative with respect to x of f of x divided by g of x, so two functions divided, is f prime of x times g of x minus f of x times g prime of x, divided by the original denominator squared. Looks very similar to the product rule, except for the negative in between the two functions in the numerator. So in the product rule, we have the advantage of it not really mattering which order we do the derivatives. As long as we do the derivative of one function times the other, plus the derivative of the other times first function, like it doesn't matter what order we do that in. But in the quotient rule, it makes a difference because that minus, you could end up with the negative of the function you were supposed to come up with. So you have to be careful. But we're not going to go through a proof. You're probably thankful for that. And the reason is it's not all that different from the proof of the product rule. And there are actually better proofs of these, but you have to have more advanced mathematics than we have at this particular point in time. And so I'm not going to go through another proof that's pretty much the same as the product rule proof. What I want to do is help you learn how to apply the quotient rule. So we're going to work through a couple of examples together, and that'll be it. So starting with the function f of x equals 3x to the fourth times 5x to the 5x minus 1. Okay, so here's the thing. Actually, let me stop right there. It matters that you do the derivative of the numerator function first times the denominator. And as long as you can remember that that's the case, you're fine. That's really all that really makes a difference. There's lots of different mnemonics. There's one like that's pretty common, Hody hi minus Heidi ho, that sort of thing. I'm not really great with those kind of mnemonics. For me personally, what I do is I have this box that I use, and I'll show you it and show you how it works for me. Whatever method you use to get the numerator correct for the quotient rule, I am fine with. Don't worry a bit about it. So what I do is I establish a box like this, and I put my numerator here, my denominator here. Then I find the derivative of each of those and put those here and here. And all I have to remember is to multiply these two functions first. Okay? And as long as I do it that way, I'm good. Okay? So that's what I do, and if that works for you, great. If you have a different method of remembering, that's fine as well. But so what I would do then is make up a box over here. The numerator is 3x to the fourth. The denominator is 5x minus 1. So then the derivative of the numerator is 12x cubed. The derivative of the denominator is 5. I just need to make sure I multiply these two functions first. So the derivative of f is going to be 12x cubed times the quantity 5x minus 1 minus 3x to the fourth times 5. And then don't forget that you're dividing by the original denominator squared. Now, in terms of simplification, different instructors are going to have different rules on that. Some instructors just want to see that you can apply these rules, and they don't care if you simplify at all. Other instructors want you to simplify everything. I'm going to simplify as much as I can, and that way you can see how to simplify. But if your instructor doesn't require it, then close your eyes and put on earmuffs for a few seconds. Whatever you want to do. Now, the numerator could be simplified by just multiplying the 12x cubed through and then doing the 5 times the 3x to the fourth. So 12 times 5 is 60. X cubed times x is x to the fourth power. So then 12x cubed times negative 1 would be minus 12x cubed and minus 15x to the fourth. Then in the denominator, I'm not going to expand that denominator because often it's the factored form that's considered the simplest form. So it's already factored, just leave it as is. The numerator, I now have like terms of x to the fourth. So 60x to the fourth minus 15x to the fourth would be 45x to the fourth. And then minus 12x cubed divided by 5x minus 1 quantity squared. At this point, you could factor out x cubed from the two terms in the numerator. That might be considered simpler. It might be considered simpler to leave it as is. It's arguable at this point, but this is probably an acceptable answer for any instructor that you have. Next up, g of x equals x squared minus 5x over 2 minus x. So let's try it out. Again, like I said, I do this box. The numerator is x squared minus 5x. The denominator is 2 minus x. So the derivative of the numerator is 2x minus 5. Derivative of the denominator is negative 1. We multiply these corners of the box first. So g prime of x is going to be 2x minus 5 times 2 minus x minus x squared minus 5x times negative 1 all over my original denominator squared. All right, so simple simplifications first. I think all instructors would want you to do this. This negative and this negative 1 would make a positive. That's easy enough to do. That might be all that's required for your particular instructor. Others might want you to simplify the numerator a bit more. So if that's the case, start foiling the first two terms. So 2x times 2 is 4x. 2x times negative x is negative 2x squared. Negative 5 times 2 is negative 10. And then negative 5 times negative x is positive 5x. In the other term, I would still have x squared minus 5x because those parentheses are no longer necessary. The denominator I'll leave alone because it's already factored. And let's see, in the numerator I could have, so negative 2x squared plus x squared would be negative x squared. 5x and negative 5x, those cancel each other out, that's nice. And that leaves me still a positive 4x though, so 4x there. And then a minus 10 all over 2 minus x quantity squared. And that right there should potentially be enough. Sometimes instructors have the requirement that a leading term coefficient shouldn't be negative. That's easy enough to fix. You just factor out a negative from the numerator and make it x squared minus 4x plus 10 all over 2 minus x quantity squared. So again, it's kind of arguable as to which of those forms is the simplest. Just ask your instructor what their expectations are for your course.